For a very brief recap of what we covered on Monday, we talked about the transmission line as a device to deliver electrical power from the generator side to the user side. So the transmission line can be very long, so we need to properly formulate it in order to solve it. So we want to know everything about the voltage and current as a function of space along the transmission line. So for any given position, we want to know its full information, voltage and current. All right, so we defined on Monday a reflection coefficient. Okay, so the reflection coefficient is purely defined by the impedance mismatch of the load impedance to the characteristic impedance of the transmission line. So once we know the reflection coefficient, we basically know how much voltage for the backward propagating wave is related to the forward, the incoming voltage amplitude, right? So let me walk you through again, covered on Monday. So eventually, this is the system we want to solve. We have a generator with its own intrinsic impedance, and then the generator is connected to the transmission line. It's very long. It's very long, so I omitted something. The transmission line has an intrinsic characteristic impedance, Z0, and then it's connected to a user with a load impedance, ZL. Right? So for simplicity, we defined at the user end, we have Z equals 0. But at the same time, we also want to define a new directional variable, D, which is in the negative direction of Z. So both D and Z coordinates have 0 at the user end. So this is for simplicity, as we talked about on Monday. For the equations here, we want to plug Z equals to 0 in this 4 parameters. So the mathematical derivation will be much easier, right? Okay, so the entire essence is, if you want to understand about a transmission line, everything, geometry, material, would provide some kind of contribution to the transmission line. And all you need to understand about transmission line itself, those are covered by the complex propagation constant and the characteristic impedance. So once you know these two parameters, you know probably everything. You know the operational frequency, of course, and gamma, you know your effective wavelength, and you know your characteristic impedance. You pretty much know your reflection coefficient. All right? So the entire process flow was starting from the KCl, KVL equations. We were able to write down 2 mathematical equations, but we have 4 unknowns to be solved. 2 voltage amplitudes and 2 current amplitudes. But somehow, because due to the beauty of the transmission line intrinsic behavior, voltage and current for a given wave is fixed. It's having a fixed relationship. And that relationship is the characteristic impedance. Okay, so once we know this, we can represent currents as a fraction of the voltage amplitude. So we knock down 2 unknowns. So we only need to solve for the amplitude of the voltage, and that's it. Okay, so now the number of unknowns is reduced to 2. And at the user end, and starting from those two equations, we were able to know how much of the voltage amplitude is being reflected. And that reflected wave is your source for your backward propagating voltage wave. So, in the end, we only have one remaining parameter to be solved, V0 plus, the forward voltage amplitude. Okay? So, is the reflection coefficient completely new to you? If you look at the expression, the load impedance minus the characteristic impedance, and then divided by the sum, if you think back in high school, this is something you learned already. If you have two different materials with different refractive indices, if you have a wave coming in, you have partial transmission and partial reflection. The mathematical formula is identical to this one. So the reflection coefficient that you learned in the past is n2 plus minus n1, n2 plus n1. So they are identical. Okay? So this is nothing new to you. You should have prior knowledge to this derivation. So the same expression for the reflection coefficient can be normalized. So everything normalized by the characteristic impedance. So I'm denoting ZL, the load. If it's normalized or divided by the characteristic impedance, I added a bar on top. Okay, so this is merely mathematical rewriting. Okay, so let's come back to what we want to cover today. Before I go on, I really want to convince you, throughout this course, all the calculations require special care. Okay? So I want to give you a taste of flavor. So if my load impedance is having a simple resistor connected in series with a capacitor, I know the resistance value, I know the capacitance value, and I already know my operational frequency. Are you able to calculate the resulting reflection coefficient? To tell you the truth, I can't really do it on the board, so I have to take my note. Okay? But throughout the process, I want to show you in the future, when you work on the homework problems and when you're trying to answer examination problems, you need to use a nice calculator. Okay? So let's try to solve this case. A resistor connected in series with a capacitor. So first, we need to write down its load impedance value. For some of you who don't really remember how to write down the impedance for a capacitor, let me refresh your memory. All that we learned in the past is if we have a time-varying voltage across the capacitor, then we induce some time-varying current. And that current flowing across the capacitor is I equals C, the capacitance, and multiplied by the time derivative of the voltage. Okay? So if I write that down in phasor notation, now I in the phasor domain is equal to j omega c times the voltage in the phasor domain. Why? Because again, whenever we have a temporal derivative transformed into the phasor domain, we multiply it by j omega. Okay? So the impedance for a capacitor, which is defined by the voltage divided by current, is now as negative j divided by omega c. So basically, it has a purely imaginary impedance and is negative. So in the future, whenever you view a circuitry with an effective impedance, the imaginary part, if it's negative, it can always be represented by a capacitor. On the other hand, if the imaginary part of the impedance is positive, then it represents an inductor, right? So, ZL in this case is 50 ohms minus J divided by omega is 2 pi times 10 to the 8th, and the capacitance 10 picofarad. Do you happen to know how much pico stands for? Probably not. Pico means 10 to the minus 12. Okay? Pico, 10 times minus 12. Alright? So this is where I really need to define it. Alright, so basically the low impedance is a complex value. So this is where you have to think. You learned about complex numbers. You need to also be a master in processing them, right? So we know the Z load, so now the gamma V is simply the load impedance and minus characteristic impedance, load plus characteristic impedance. So in this case, the characteristic impedance is 100 ohms, right? As you can see, you have the flavor already. It's just tedious. Okay, so each year I really hate this, but I have to do it just to let you know you have to be extremely careful in processing these numbers. So at this moment, do you know how to go on? If you have a complex number, the easiest way is to calculate its amplitude and its phase, right? Eventually we're working in the phasor domain. So, without further complication, so I'm trying my best. As I promised, this class is not meant for mathematical derivations, but I really want to give you a heads up. In dealing with all these calculations, you have to be extremely careful. Okay? So in the end, the reflection coefficient is having some kind of amplitude. The amplitude is 0.76. Is it reasonable? So you have to think, reflection coefficient must be bounded by a certain value, right? The amplitude should be less than 1, because a reflection coefficient 1 means 100% of the power is being reflected. And what is its minimum value in terms of amplitude? The smallest reflection coefficient amplitude should be 0, right? Nothing is being reflected. Okay? So the reflection coefficient, its amplitude should be bounded between 0 and 1. Okay? Now the phase can wander within 2 pi, 360 degrees. Okay, so this is some kind of valid reflection coefficient. So I jumped through some kind of processes, but for you, it's just to get a flavor. Okay? You need to master the calculation of complex numbers. There are a lot of potential loads. Okay? So the one we calculated was having the real part and imaginary part. You can also have purely imaginary load, or you can have a shorted load, short circuit, or you can have open circuit, right? And purely inductive, purely capacitive loads. So all these would give you a different reflection coefficient in terms of its amplitude and phase responses. All right, so this page, probably different loads are going to appear in your examination. And by the way, homework number 1 is already out, so you are encouraged to start working on the homework problems. Right? So you will get chances to practice in dealing with complex numbers. All right, so I don't want to jump into solving everything just now. I want to emphasize on the physics of having forward propagation wave and backward propagation wave. As we mentioned, when we have forward and backward propagating waves, we will have standing waves, 驻波, right? Standing waves. Of course, we're very happy. We only have the left, the single unknown left, V0 plus. But let's talk about standing wave in more details. So we know that the reflected wave, its amplitude is somehow related to the input voltage amplitude at the load, right? Due to impedance mismatch, you have partial reflection. So this is how the reflected voltage amplitude is related to the input voltage amplitude. And these two are the equations we are relying on, right? So now the voltage in the dimension of D, remember, D is negative Z, nothing more. It's just negative Z, nothing more. Okay? So I can write voltage phasor as a function of space, but now the space is in D rather than Z. D equals negative Z. Current phasor as a function of space. So I have these two equations. Now the question is, once I have forward and backward propagating waves, what is that doing to my transmission line propagation behavior? How does it change the voltage and current as a function of space? Okay. So eventually I will try to derive this, the first equation for you. The second equation is left for you to function as one of your practice. It's not a homework, it's just practice. Okay? So remember, we're trying to talk about standing waves now. Okay? I need to do some more derivation again. So I want to remind you again, the reflection coefficient itself is a complex value, as I showed you on the left. Right? So it's easier for me to define the reflection coefficient or rewrite it using its amplitude and phase. Okay. So you know it has an amplitude and a phase, right? So now I can rewrite V as a function of D is D0 plus E J beta D plus so I'm only trying to rewrite this one with its amplitude and its phase. So I have a double negative so that recovers the phase to a positive L. Okay. So when we have a standing wave, what we really care about is the maximum value of voltage allowed for each single location. So we want to know this guy's amplitude. Okay. So this D's amplitude can be written as so you have to think, what does this equation stands for? Voltage phasor itself is a complex number in general. Okay? So this means the complex number multiplied by its complex conjugate, taking a square root, is its absolute value. You can think of A plus JB, right? This is your complex number. You multiply by A minus JB, its complex amplitude, and then you have A squared plus B squared, right? So if you take a square root, that is the absolute value, the amplitude of original complex number. Okay. So let me erase this one. So it's better for you to really work on your own for now. As I work on the derivation using this definition, it's also good for you to write on your own. So then we can compare, we can cross-compare. So this one multiplied by this one gives you V0 plus absolute value squared. So I remove that out of the square root. The first term multiplied by the first term gives you 1. Okay. The second term in the parenthesis multiplied by the second term in the parenthesis. So these exponential terms are cancelled. So you only have gamma V absolute value squared. And then I have to treat the cross terms. This one multiplied by this one, and this one multiplied by this one. Okay, so let's do it. This one. So this one multiplied by this one gives you negative j 2 beta d. Okay? 2 beta d. Plus gamma b. And this one multiplied by this one gives you 2 positive j beta. So if we take a look at these two terms are having the same amplitude, but the only difference is in the phasor. The phases, one is positive, one is negative. This is something you should know, because exponential j beta plus exponential negative j beta is 2 times cosine. 2 cosine theta, right? So we know that this is B0 plus multiply 1 plus gamma B squared plus 2 times So if you compare to the first equation written down in the PowerPoint, I'm not too bad. I did the derivation correctly. So, as I mentioned, emphasized over and over, the mathematical derivation is not my main point. The main point for every mathematical derivation is you have to understand the meaning behind these equations. So now we can take a close look at this equation. What does it mean? It means along the transmission line, whenever you have a non-zero reflection coefficient, which means you have some kind of impedance mismatch, ZL is not equal to Z0, and then you have a non-zero reflection coefficient. So that gives rise to simultaneously having forward and backward propagated wave. So that is going to change your maximum allowed voltage along the transmission line. And that maximum allowed voltage is exactly this. The voltage, the total voltage phasor as a function of space, absolute value. Okay? And that maximum allowed voltage changes against location in the form of cosine. So basically, you anticipate to have cosine oscillations or sinusoidal oscillations. All right, so try the second one on your own. It's similar. It's only just changing some plus to minus, and then you divide by the characteristic impedance. Nothing else.